Today I'm going to present a SHiFT, semi-hosted fast testing for embedded applications, which, as Mary said, this is a collaboration with my colleagues from Northeastern University and Florida International University. So embedded devices are quite important nowadays because they are using in the industry, medical devices, smart homes, and cars, right? They are everywhere, and they are supporting many of the businesses that right now are around the world, right? So because of the importance of these devices, we have seen many attacks on these devices, and we can say that because of these devices are vulnerable in some ways. There are other critical infrastructure that is under risk, right? Because they are integrated in many ways. So the question is why identifying vulnerabilities in these devices is quite challenging. There are essentially three main components. So the first one is the diversity of software and hardware in these devices. Compared to standard computers, they don't have a single operating system, or they don't have a single architecture, so it's quite diverse in terms of hardware and software. In terms of the minimalistic design, and specifically for this project that focus on deeply embedded devices based on microcontrollers, these devices don't have hardware primitives that are available in standard computers, like memory management unit, for example. And the third one is the computing and operational constraints, because these devices are usually optimized to work on real-time operations or even being powered by batteries, right? So these are some of the constraints that make finding vulnerabilities in these devices challenging. So what is the state of the art and how the community is trying to solve this is based on what is called rehosting. So rehosting essentially is to rehost the firmware from the MCU to a powerful workstation of computer where we can execute the firmware and also conduct some analysis, for example, Fuzz testing, right? And this is based on emulation and some hardware synthesis that essentially uses the same firmware and emulation based with some heuristics and so on to create an environment where the firmware can be executed. But there are some limitations with this approach, right? Because we are going to have a firmware that is essentially vulnerable or buggy, and then we use the same firmware to generate hardware to execute. So that is limited, right? This is reflected in some issues related to reduced fidelity, reduced observability, because some of the crashes that eventually are triggered in these platforms cannot be observed, and also limited compatibility because the complexity of some peripherals cannot be synthesized just from observing the execution of this firmware in these emulated environments. So to solve these challenges, we propose a new architecture where now the execution and the analysis is conducted directly on the MCU, and this is only going to consume some fuzzing facilities that are running in a workstation, right? And this is based on in a simple paradigm that is called semi-hosting. This has been used in the industry for quality tests and for many other cases, but not specifically for security, right? So this is the novel part of this approach. So this is the architecture that we propose. So essentially, we have a workstation that is going to provide only the mutated input to a fuzzer that is running on a cluster of MCUs, right? And these MCUs, so essentially within this MCU, we have two components: a monitor that is what we have in a normal computer, which is a fuzzer, a complete fuzzer, but without the fuzzing engine, right? Just the mutating engine is running in the computer. And also we have a target. The target essentially is what we are going to test here. And it could be another task, taking advantage of a multitasking environment, or it could be another core. So one core of the MCU is going to run the fuzzer, and the target application is going to be running another core. So it's very flexible, right? And this is meant for in-house testing. So the idea is that we are going to take advantage of the source code, and developers can integrate this tool early during the development and design phases, right? The idea is that this solution should support desktop-level instrumentation. So if a developer is already comfortable using tools and instrumentation that is available in desktop computers, the idea is that we provide similar characteristics without too many changes. It should be also compatible with a standard development platform, so we don't need a special hardware or things that are not commercially available or are too expensive that are going to affect the development cycle of these devices. So to support this solution, there are some challenges that we need to solve because, as I mentioned earlier, these MCUs don't have all the capabilities that we have in desktop computer, like the memory management unit. And one of the main challenges to support instrumentation is that we don't have the memory management unit, right? For example, to support here ASAN, the ASAN uses shadow memory, which is calculated automatically calculated to a physical address using hardware, right? So essentially, the memory areas can be in any place, and then they are going to be allocated in a real place where it can work. In an MCU, because we don't have memory management unit, when we have this sort of transformation to the shadow memory, then this is going to point to illegal memory regions, right, or reserved memory regions. So this is not going to work. So what we did here is to create a very specific offset in such a way that we organized memory areas, including the read-only memory areas in RAM. And then based on this specific mapping, we were able to implement ASAN without an MMU and still support desktop-level instrumentation in an MCU, right? Okay. Another optimization that we have to do is that because these devices have very little memory, we have to reduce the traces that are collected, right? So we implemented an optimized method to collect these traces when the firmware is being executed on the MCU. And instead of sending the whole bitmap of the execution for coverage, we build this coverage dynamically. And we observed that this is actually quite effective because instead of sending the whole bitmap, we are only sending a few bytes. And this is enough, with enough information to reconstruct that on the desktop computer, and the desktop computer can mutate again the input and then provide a new fuzzing input, right? So as we can see here, the whole fuzzer is running directly on the MCU, but we are only consuming the mutating input from the desktop computer. For implementation, we have fully tested prototypes for ARMv7, ARMv8, and the Extensa architecture, and we also test compatibility with other architectures that I am going to talk a little bit later. And also we implemented a universal serial proxy that can support AFL, AFL++, or any other modern mutating engine. So this is totally independent. For the firmware, we use FreeRTOS with some kernel extensions. We also for the instrumentation, we use a GNU ARM 10.3, which is open source. So we modified a little bit the runtime, and also a tailored GCC compiler for the ASAN offset that I talked earlier. Okay, so in terms of evaluation, we verified that this approach is compatible with 12 very popular embedded architectures. Only we have some issues with the AVR, which is fine, I believe, because this is a legacy architecture, not very popular right now for IoT devices, right? But yeah, this is actually a very good result. In terms of fidelity, we observed that our approach is obviously superior in terms of fidelity to all the emulated-based solutions, and is only comparable with other solutions that also use the hardware directly to fuzz firmware directly on the device. In terms of synthetic raw performance, here we compare directly just fuzzing a synthetic firmware on the MCU and running AFL natively on a desktop computer, and we observe that we obtain even that our approach is even faster than a desktop computer. And the reason here is because the context switch is quite fast. This is pre-RTOS is just a lightweight operating system, so that is the reason that when we compare a standard ASAN running in a desktop computer with the MCU can be even faster than desktop. Okay, now we compare our solution with the state of the art. In this case, we found 5 new vulnerabilities with no false positives. Our solution is even 100 faster times than emulated-based solutions, and also solutions that use the hardware to fuzz these devices. And the important part here, as you can see, that we don't have false positives because of the instrumentation and because we are using the real hardware. We don't have any emulation here. This is an example of how we use our development environment. As you can see here, we have 2 cores. Actually, this is the dual core operation when one core is passing the other core. So here we have about CAN bus transceivers. This is a real application, and we can see here we have the highest fidelity because we are using the real hardware. Because of these characteristics, we find, as I said previously, 5 new vulnerabilities. And each one is, you can see here that this cannot be identified by regular emulated solutions because of fidelity, lack of compatibility with complex peripherals, and observability. Because in some cases, even if the fuzzer is able to trigger these vulnerabilities, they are not able to catch and essentially the firmware is going to crash later, so it's very difficult to identify where the bug is actually located, right? And yeah, the last case, the FreeRTOS, is quite interesting because we found that in the FreeRTOS kernel, which is developed by AWS and is impacting many, many devices. Conclusion, testing embedded devices require holistic methods that consider software and hardware diversity, minimalistic designs, and operational constraints. SHiFT is a novel semi-hosted framework to enable fast testing on development platforms with high fidelity, and SHiFT helped to identify unknown vulnerabilities in realistic scenarios not supported by emulated solutions. So thank you very much, and I will take any questions that you might have.